Unit 5, Hydraulic and Pneumatic Systems. Lesson 13, Pressure. We're going to start by describing the properties of fluids. A fluid is a substance that flows and takes the shape of its container. It cannot be formed into irregular piles like sand. Examples of fluids are both liquids and gases. We're going to be studying both hydraulic systems and pneumatic systems. So let's define each of those. Hydraulics is the science and technology of the mechanical properties of water and other fluids. A hydraulic system is a mechanical system that operates using a liquid under pressure, whereas pneumatics are the science and technology of the mechanical properties of air and other gases. A pneumatic system is a mechanical system that operates using gas under pressure. So let's distinguish between the two. Hydraulics deal with systems that use water and fluids under pressure, and pneumatics deal with air and other gases under pressure. In order to study these, we must understand the physical property of density and compressibility. Density is defined as a substance's mass per unit volume. Density is a physical property of matter and does not depend on the amount or size of the sample. The equation for density is D is equal to M divided by V. Where density is measured in kilograms per meter cubed. Or grams per milliliter for liquids, or grams per centimeter for solids. M is the mass, measured in kilograms or grams. You must be consistent with the other units that are present in the equation or in a question. So if you're dealing in kilograms, make sure everything's in kilograms. If you're dealing in grams, make sure everything's in grams. And finally, V is the volume. And it can be in meters cubed, centimeters cubed for solids, or milliliters or liters for liquids. Every substance has its own unique density. It's a characteristic property that belongs to only that particular pure substance. Here's a table that shows the density of common substances. What you need to be familiar with is the density of water, which is 1 gram per centimeter cubed, or 1 gram per milliliter, or 1,000 kilograms per meter cubed. This is the only one that you really need to remember, and it's an easy one to remember. As I mentioned, it's equal to 1 gram per centimeter cubed. Okay, let's try a question. A certain liquid has a volume of 75 milliliters and a mass of 40 grams. The density of the liquid is, so we're given the volume, 75 milliliters, and we're given the mass, 40 grams. So density is equal to mass divided by volume. That's 40 grams divided by 75 milliliters. If we punch this into our calculator, 40 divided by 75, we end up with a density of 0.53 grams per milliliter. Compressibility is the ability to press particles of matter closer together. Gases are the most compressible. And solids are the least compressible. order to study hydraulics and pneumatics, we have to understand pressure. Pressure is defined as the magnitude of the force per unit area, and the unit is the Pascal, given the symbol capital P small a. 1 Pascal is equivalent to 1 Newton per meter squared. So our equation for pressure is pressure is equal to force over area. Where P stands for pressure and it's measured in pascals, force is measured in newtons, and area is measured in meters squared. Just so you can understand and experience in real life what 1 Pascal is equivalent to, it's equal to the pressure exerted by a single sheet of newspaper resting flat on a table. So I'm sure you can remember that and kind of understand what that feeling is. Let's do a first example. Example number 1. A crate is 2 meters wide, 3 meters long, and 1 meter high. The magnitude of its weight, i.e. the force of gravity, is 1.2 times 10 to the power of 4 newtons. So I'm going to draw a quick diagram of what this looks like. So we have 2 meters wide, 3 meters long, and 1 meter high. So when we're looking at the pressure that this exerts on a surface, what we're looking at is the surface area here, and the area can be calculated using length times width, which is 2 meters times, that's this, times 3 meters. If you punch this into your calculator, you end up with an area of 6.0 meters squared. So that's the area of the crate in contact with the floor. This is part A. In part B, they want us to find the pressure, which is equal to the force divided by the area. We're given the force above, it's 1.2 times 10 to the power of 4 newtons, divided by an area of 6.0 meters squared. So we're going to punch this into our calculator. Punch it in carefully so that you get the proper scientific notation. We have 1.2 to the power of 4 newtons divided by 6.0 meters per second squared. We end up with a pressure of 2,000 pascals. And we want to make sure we use a capital P. Now you could divide this by 1,000 and convert it into kilopascals. So if you divide that by 1,000, you end up with 2 kilopascals. All right. Let's look at hydrostatic pressure in fluids. Consider the balloon shown in the diagram. In order to inflate the balloon, air must be blown in under pressure. Once inside the balloon, the air particles will distribute themselves roughly evenly throughout the balloon, and their state of continuous motion means that they will bump into the sides of the balloon. This creates pressure on the sides of the balloon, keeping it inflated. Similarly, this is experienced by liquids as well. When a liquid is in a container, for example, a liquid such as water in a glass, will exert pressure on all surfaces, again due to the motion of the particles of the water bumping into the sides and the bottom of the glass. those surfaces apply an equal and opposite pressure on the water in order to contain it. Unlike the balloon example, the pressure is not the same everywhere in the glass of the water. The pressure exerted will be greater at the bottom and it will be less at the top. This is indicated by the diagram with the sizes of the arrows. So we have large arrows here at the bottom and small arrows here on top. Anyone who has ever dived below the surface of the water can attest to the fact that the pressure exerted by water increases as you dive deeper. The pressure is higher at deeper depths because the weight of all the water above it. The name given to the pressure exerted by a fluid that is not moving is called hydrostatic pressure. Hydrostatic pressure increases at a very predictable rate as depth increases for incompressible fluids or liquids. The hydrostatic pressure at a given point in a liquid can be calculated using the following formula. P is equal to dHg. Where P is the pressure, measured in pascals, D is the density, measured in kilograms per meter cubed, and G is something that we've seen before. G is the gravitational constant. Because if you imagine, as you go deeper down into water, the force of gravity of the water particles, the deeper you go, gets stronger and stronger. So we're going to be using gravity to help us in our calculations. And H in this equation stands for the height or the depth below the surface. Let's try an example. Calculate the hydrostatic pressure on a scuba diver at a depth of 12 meters. The density of seawater is 1,025 kilograms per meter cubed. So we'll write down everything that's given in this question. We're given the depth or the height, which is 12 meters. The density of seawater is 1,025 kilograms per meter cubed. Notice that this density is slightly higher than the density of pure water. The density of pure water is only 1,000 kilograms per meter cubed. We know G is 9.8 newtons per kilogram. This does not change near the surface of the earth. So to calculate the pressure, it's equal to dHg. So let's sub these in. That's 1,025 kilograms per meter cubed times 12 meters times 9.8 newtons per kilogram. Let's punch this in to our calculator. Make sure you punch it in carefully. Take your time. That's 1,025 times 12 times 9.8. We end up with 120,540 pascals, or 121 kilopascals if we round. So to go from pascals to kilopascals, what I did was divide by 1,000. And if you wanted to go in the opposite direction, you would multiply by 1,000. You can measure pressure using an altimeter. It's an instrument that uses atmospheric pressure to determine the altitude of an airplane above sea level. You can also measure pressure using a barometer. It's an instrument that measures atmospheric pressure. They're filled with liquids, a container that's filled with a liquid, and that liquid forces, as air pressure presses down on this liquid, it's going to force liquid up this vacuum tube. The higher the pressure, the higher the level inside the vacuum tube. An aneroid barometer is an instrument that measures atmospheric pressure without the use of a liquid. If you take a look at this diagram, we have a bunch of different shapes. And you notice that regardless of the shape, that the liquid reaches the same level since all of these are open to the atmosphere. So regardless of the shape or the path, you will find that these lead or seek its same level. And the same is true here. Now there's an important and interesting fun fact about hydrostatic pressure. The atmospheric pressure at a specific altitude limits the height to which water can be pumped from a well using a suction pump. The maximum height that water can be pumped to is 10.3 meters. Thus, with a well-made pump, a water well can be no deeper than 10.3 meters. And as we mentioned earlier, water seeks its own level. The liquid in vessels that are attached to the connected vessels remain constant. So you can see whatever shape this path would have taken, water will always seek its level here. And this level matches the level of the container of water. If you want to measure gauge pressure, and that's the pressure of a hydraulic or pneumatic system, we have to use devices that measure pressures in liquids and gases. They don't measure the absolute pressure. What we measure instead is called the gauge pressure. And it's the difference between the absolute pressure and the atmospheric pressure. Because regardless of what's going on inside of the container, what happens on the outside is important as well. So in order to find gauge pressure, it's equal to the absolute pressure minus the atmospheric pressure. And you can actually rearrange this equation and find an equation for absolute pressure as well, which is equal to the gauge pressure plus the atmospheric pressure. One of the types of instruments that is used to measure gauge pressure is called a manometer. And this diagram shows how a manometer is used. If the pressure on one side increases, the water level on that side will go down, while the water level on the other side goes up, and I'll explain with the diagram how this is happening. So here we have a U-shaped tube, and it's filled with water, and the water is equal on both levels because both of these are open to the atmosphere. But if we attach one side to, let's say, a tank that is under pressure, what it's going to do is force this water level down, and as a result, force this water level up. Now, what's important whenever you create a manometer is not how much it went down or how much it went up, but the difference in water levels between the two. Because remember, these two water levels under normal circumstances should be the same, but when you attach a hydraulic or pneumatic system to a manometer, it's going to force down this liquid and push up this liquid, and you'll get a reading of the pressure inside this system. Okay? The gauge pressure we're going to calculate using our equation, DHG, that we used above. And this is often called the static pressure head. Okay? When you find the difference in height, this area here, the difference in height caused by attaching a container under pressure to a manometer, the difference in height is called the static pressure head. Okay? Let's try an example. An air pump is connected to one tube of a manometer containing water, and water has a density of 1,000 kilograms per meter cubed. Pressure is increased until the static pressure head is 15 centimeters. What is the gauge pressure? So gauge pressure is equal to dHg, where h will be the difference in height, also known as the static pressure head, so we can calculate this using the data that we have. We know the density of water is 1,000 kilograms per meter cubed. We know h is 15 centimeters. Make sure you put 15 centimeters into meters. In order to do so, you're going to divide by 100. So we end up with 0.15 meters. And we're going to multiply this by 9.8 newtons per kilogram. That's what G is. G is equal to 9.8 newtons per kilogram on the surface of the Earth all the time. Let's punch these into our calculator and see what we get. So we have 1,000 times 0.15 times 9.8. It's equal to 1,470 Pascal. So that's the gauge pressure of this air pump. Let's try another example. Calculate the absolute pressure in the water behind a dam with static pressure head of 18 meters when the atmospheric pressure at the dam's location is 100 kilopascal. Okay, so let's see what information we're given. We know the static pressure head is 18 meters, so we write H equals 18.0 meters. We know the atmospheric pressure is 100 kilopascals. And what they want us to find is the absolute pressure. First, we'll need to find the gauge pressure. And gauge pressure is equal to dHg, where d is the density. In this case, we're looking at water, which is 1,000 kilograms per meter cubed. H is the static pressure head, 18 meters, and G is 9.8 newtons per kilogram, and that is constant near the surface of the Earth. So let's punch this into our calculator and find the gauge pressure for this dam. So that's 1,000 times 18 times 9.8. So we end up with 176,400 Pascal. That can also be written as 176.4 kilopascal. Now, in order to find the absolute pressure, we're going to use the equation above. P absolute is equal to gauge pressure plus atmospheric pressure. So if we punch in the gauge pressure at 176.4 kilopascals and the atmospheric pressure at 100 kilopascals, we end up with a total of 276.4 kilopascals. So the absolute pressure at the dam, in the water behind the dam, is 276.4 kilopascals. So there are two things that are contributing to the pressure that the dam wall must support. Number one, it's the amount of liquid and the height of which it is being stored behind the dam, and that we call the gauge pressure. And number two, it also depends on the pressure of the atmosphere itself, the pressure of the air, because it will provide additional pressure onto the body of water that is behind that dam. So if you add the two up, you'll get the absolute pressure. What I want you to do is try the homework practice questions that are outlined below, and when you're done, you can work on the LMS quiz for this corresponding section. Good luck.